The square root of 2. Why it matters. This story is a bit of a math fairy tale that mathematicians like to tell our kids at bedtime. As a story about history, it might not be completely true, but as a story about math, it is. Once upon a time, more than 2,000 years ago, the ancient Greeks loved to study math. They especially loved geometry, and they loved rational numbers as well. A rational number is just a fraction, like 2/3 or 1,007ths or -6/15. It's an integer, call it p, divided by another integer, call it q. The number on the bottom can't be 0 because we can't divide by 0, at least not yet. But all other integers are fair game. The Greeks loved rational numbers. They liked how they were neat and clean and easy to write down. And the Greeks had a certain belief about rational numbers that made them particularly happy. They thought that all numbers were rational. They didn't know how to prove it, but it seemed like a reasonable enough thing to think. And the implications as they saw them were that since all numbers were rational, it must mean that the universe itself was fundamentally rational. Neat, clean, well-organized, easily cataloged. It does seem reasonable to think that all numbers are rational, partly because whenever you pick two different rational numbers, you can always find a third rational number in between them by taking their average. If you then pick the first rational number and then average, you can take their average again, and so on. And in this way you can actually find an infinite number of different rational numbers, all in this little interval. In other words, rational numbers are everywhere. They're impossible to avoid. And even if you're not a fan of fractions, it can be comforting to think that all numbers are rational. It would mean that if someone hands you a totally weird number which is not remotely an integer, then you can always add that number to itself some number of times and get an integer, neat and clean. But unfortunately for the Greeks, it turned out they were wrong. Someone found a number that could never, ever be written as p over q, where p and q were both integers. That number was the square root of 2. We'll talk soon about how we know the square root of 2 isn't rational, but first let's talk about why we care. Why should the square root of 2 even be a number in the first place? Can't we just leave it out? And yes, we can. As mathematicians, we can kind of do whatever we want as long as it's internally consistent. We can make up crazy-seeming systems of numbers, give them rules to follow, and see what happens. We can certainly decide that the only numbers we care about are rational numbers, and if anything else wants to be a number, then that's just too bad. There are a few things we miss with this approach, however. For one thing, we can sort the set of rational numbers into two pieces. The set of rational numbers which are positive and whose squares are greater than 2, and the set of rational numbers that don't fit in that category. This cuts our rational number line in two pieces, but since the square root of 2 isn't rational, there's nothing at the break sticking these two pieces together. This number system has a hole, so if we want to stick with rational numbers, we need to be all right with a number line with holes. Another benefit to including the square root of 2 in your number system is that it happens to be very useful, especially if you want to do geometry, which the Greeks did. In particular, suppose you have a square with side length 1, and you want to find the length of its diagonal. You can use the Pythagorean theorem if you know it, but it's actually not necessary in this case. You can do this particular calculation by drawing pictures. First, take 4 such squares and put them all together to make one big square with side length 2. We can draw a smaller, slanty square inside it, like so. The side lengths of this square are the number we want to know, the length of that original diagonal. What's the area of this slanty square? Well, suppose we shade the inside red and the rest blue. There are 4 red triangles inside the slanty square and 4 blue triangles outside it. And these triangles are all the same shape. They're all right triangles that we get by cutting a 1x1 square in half. This shows us that the area of the slanty square is half the area of the big square. And the big square is 2x2, so it has area 4. Thus the slanty square has area 2. So how long are its sides then? They must be the square root of that area, so the square root of 2. This shows us that this particular number is hard to avoid. How can you use numbers to study a square if the length of its diagonal doesn't even count as a number? It's not going to work. You need at least some number systems that include the square root of 2. And as we'll see next time, that number is decidedly not rational.